Okay, guys, so what we're going to talk about in this video is sampling variability and sampling distribution. Fairly easy concept to understand. Essentially, what we want to understand is how we can use X bar or our sample mean um, to be able to make an accurate estimate of your population mean. What we need to understand is that if we were to take a second random sample from a larger population at the same time as you took your first, it would be significantly different because you would choose, well, maybe not significantly, I shouldn't say that, but it would be different because you would be choosing um, a different sample, and so likely you would produce a different sample mean. And so we need to understand, probably, I should say, what is the best way for us to find our sampling distribution. What we're talking about here is the idea of sampling variability. So how can X bar or our sample mean be an accurate estimate of our population mean? After all, different random samples would produce different values of your different sample means. The basic fact is called a sampling variability. The value of a statistic varies in repeated random sampling. So what we're going to do to make sense of sampling variability, we're going to ask ourselves, what would happen if we took many samples? So instead of just taking one sample of, say, 60,000 households for our population of 121 million Americans, what if we were to take, say, 500 samples? Um, Here's how we're going to do that. We're going to take a large number of samples from the population. We're going to calculate a statistic, usually your sample mean or sample proportion, for each of the samples. After that, you're going to put them together, usually in a dot plot, but in a graph of values of the statistic. After that, we're going to, as we always do, examine the distribution displayed in the graph for shape, center, and spread, as well as possibly any outliers or unusual features. So this is going to be an activity that we're going to do in class, just to kind of demonstrate the idea of our sampling variability and where we're going with that. So I had a big bin and it had 200 colored chips. 100 of them were red. The parameter is the actual proportion of red chips in the population, so therefore your parameter was 0.50. So what we were going to do is everybody was going to take a sample size of 20. So assuming that everybody was in class, we were going to have 20 samples of 20. So after one student grabbed out 20, you're going to count your sample proportion. So suppose you had 8 out of your 20 chips were red, your sample proportion would be 8 out of 20. You're going to pass them to the next person. They were going to take out their 20 chips, count out their red. Let's say they had 11 out of 20. Their sample proportion would be 11 out of 20, and we're going to continue doing that until everybody had it. And then we were going to put it all together in a class dot plot and describe what we saw in our distribution. However, because this turned into a video lesson, we can't do that, so here's the best thing we can do. So here is kind of a pretend example. This is actually 35 samples, so a bit more than we would have had in class, but still considered kind of a smaller sample size than taking a large sample. If you think about it, if you have 200 chips, you have a lot of different samples that can possibly be made from 200 chips. So in that aspect, you're talking 35 being pretty small in respect to how many possible random samples could actually be taken, or think of arrangements that could possibly be made from 200 chips. And so it is still kind of a smaller sample, but this will serve the purpose to get the idea of where we're going with our sample distributions. So this is the sample proportions that everybody got in the class. Um, if you notice, we'll start to talk about the distribution a little bit. So the shape is roughly symmetric. We have that single peak here, okay, which looks about the center, but the center is just shy of that. So the mean of our sample here would be 0.4. It was 0.499, so pretty close to our center, or pretty close to our peak, I should say. So our spread, or our standard deviation, was 0.112. And considering that this could possibly be an outlier, but considering that this is our standard deviation, I would say no, it's not an outlier. So again, this is only 35 SRSs. There are several that can be taken of size 20 in a population as large as 200. So if we took all of these samples and calculated if we took all of the possible samples that could be made from the 200 population, that and graph the values all together, that's what we're going to call a sampling distribution. The problem is it's just not realistic to think that you can take all of the possible samples that can be made. So you are always going to take less than what's possible, but you're simulating a sampling distribution. So the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size of the same population. So like taking 35 samples, all of size 20 from that same bin of the 200 chips. The only difference is that we're going to be taking many, many samples, so more than if your population's as big as 200 and you're taking a sample like 20, you're going to want to take way more than 35. So it's usually difficult to take all possible samples of size n to obtain the actual sampling distribution of statistics. So instead, we're going to simulate to imitate the process of taking many, many samples and create an approximate sampling distribution. So the 35 will serve its purpose because it's way more realistic to take a sample of that size than 1,000. So this is kind of what we were doing before. So assuming that this is the distribution here, let's say that you have 100 red and 100 blue chips. So one possible sample of 20 could have given you 8 out of 20 for your sample proportion. The next could have given you 11 out of 20 for your sample proportion. And then a third student could have picked, okay, putting them all together, this is many, many, many. This would be about 500 SRSs. Okay, so this is 500 SRSs, each of size 20, put together in a dot plot. And this is the idea of our sampling distribution. So the idea of simulating all of the possible samples that can actually be made. We'll back it down to something like 500, put them together in a graph, analyze our important ideas, our distribution, and use that to be able to estimate for our larger population. So just some important things here. So the population distribution gives the values of the variable for all individuals in the population. The distribution of sample data shows the values of the variable. In this case, it would be color for the individuals in the sample. The population distribution and the distribution of sample data describe individuals. A sampling distribution describes how a statistic varies in many samples of the population. That last thing we've already discussed. And now to take a look at an example. So it's the same background. We're still dealing with the 200 chips, still dealing with a size of 20 in our sample. And this time, this is the same as it's the same as this one. It's 500 SRSs. So let's talk about certain things to see kind of where we're going to make sense out of things here. So there is one dot here at 0.15 right there. We're going to explain what this value would represent. So in one SRS of 20 chips, there were 3 out of 20. So you're talking about a proportion of 3 out of 20, which is 0.15 for your proportion for just that one single sample. So let's describe now our distribution. So our shape is close to being bell-shaped. I think we could say mostly bell-shaped. Definitely looking symmetric, unimodal. Our center looks again in about that 0.5 range. Okay, our spread anywhere between 0.25 and 0.75. So 0.25 to 0.75 on our spread. And outliers possibly the 0.15. Okay. Still analyzing the same thing. Same graph, different questions. So let's think about this one. And this is kind of where, why we can use our sampling distributions to estimate or is a good description of our population. So would it be surprising to get a sample proportion of 0.85 or higher in an SRS of 20 when your sample proportion is 0.5? Well, think about it, guys. You don't have any 0.85 or higher when you took 500 samples. So yeah, I would say that it's fairly unlikely. If it didn't happen at all in 500 samples, I would say it's probably not going to happen. So suppose your teacher prepares a bag with 200 chips and claims that half of them are red. A classmate takes an SRS of 20 chips, 17 of them are red. What would you conclude about your teacher's claim and explain this? So the student's results give strong evidence against the teacher's claim. If the teacher is claiming that half of them are red, having as many as 17 come across for one student, it would kind of conclude that the teacher's claim wasn't accurate. As noted in part C, it is very unlikely that this would actually happen though, because a sample size, or a sample proportion rather, that high has never came up in 500 samples. So it's unlikely that the classmate would have chosen 17 out of 20 of them being red. And that is it for this video. So you guys now have a check your understanding. Fairly easy. I just want to clarify one thing on number 2. Number 2, I do want to point out to you guys that it does say a possible distribution. So you're essentially making up a distribution for this one, guys. So answers will absolutely vary. Okay? So do your check your understanding. It's in your notes. and we will discuss the answers in class.